Good morning, good afternoon, wherever you are around the world. This is Dr. Mohamed Nezami again with another one of my videos on a new topic, new old topic. Now, today's video, I'm going to talk about the multi-section broadband Wilkinson power dividers design and modeling. I know Wilkinson dividers are covered heavily in the literature and in an online, both video and text materials. But what I would like to do today is look at in particular cases where we are interested in multi-octave power splitters, two-way power splitters. I know we did cover the, if you go to my channel, if you go to my channel, I did cover one of my videos was on among the series of among the 5 or so videos or 4 and so videos that I covered that deals with antenna array feed networks. Okay, where we took feed networks that are based on the T-Junction and some that are based on the Wilkinson divider. And I did cover the topic of relatively narrowband Wilkinson dividers, and in particular, the unequal power division ratio design-wise. So you can refer back to this video. It's part 3 of this. I welcome you all to visit my video channel, YouTube channel videos, and sign up for the subscribe to the channel. I would appreciate that. I have covered a lot of materials on RF and microwave circuit designs. You can refer back to this, and please do subscribe to the channel. That helps spread the knowledge wider. So let's cover today's topic. We're going to talk about the design and modeling of multi-section broadband Wilkinson power dividers. Now, these power dividers, say, for instance, from 2 gigahertz to 6 gigahertz, or from 2 gigahertz to 18 gigahertz, they're usually used in such a broad bandwidth. We use them most times in the labs just to do some experimentations where instead of owning a number of these for different subbands, we would use one as a broadband. We would use it for testing purposes in the laboratories and in the research labs. Another usage of these could be in the actually in the warfare electronic systems, where you might have a system that covers the spectrum from, say, 1 gigahertz to 20 gigahertz or so. So that's another use. Now, I'm an independent RF circuit design contractor. If you like to hire my services, please do reach me at this number. I operate out of Jerash, Jordan, with I have many years of experience back in the United States before I came to settle here, semi-retire in Jordan. So you can reach me at this email as well. My rate is very reasonable. And I work with your engineers from concept to fab files, both active and passive circuits. So reach out to me if you have any design contracts. Let me know. First consultations are always free, and then we can go onward from that. So let's talk about the multi-section Wilkinson power dividers. As you may have seen, all familiar with a single section power divider, and that usually is that in a 50 ohm system, all it is just 2 lines of quarter wavelength lines of 70.7 ohm impedances for 50 ohm input and output. But where If you're trying to do a multi-section Wilkinson power divider, it gets a little bit more complicated because you have to cascade a series of these dividers and the characteristic impedances of the transforming lines. The quarter wave lines becomes a little difficult if you want to try to do it analytically. We usually follow a Chebyshev type computational type distribution of these transformers, and it's well documented. A lot of times in a graduate course in RF devices, you might derive those based on the odd and even reflection coefficients of the two-way splitter with multi-sections. But in practically, we really don't have to do that. We just get right to the point where we can use either table lookups or use computer-aided design tools. And there are various people that wrote apps to do the designs where you give it the order and it comes up with a table showing you the impedances of these quarter wave line sections and these isolation resistors as well. So, and that's what I'm going to do today. I'm not here to derive mathematically the design equations for this, but we're just going to go into an app, give it the frequency band, give it the input and output impedances, and it's going to come back and give us a solution with all the tables entries of both the lines, the quarter wave lines, and then the resistors, the isolation resistors. So you might realize by now that we use multi-sections to get a broadband response, and that's illustrated here in this diagram where you can see with a single order one, which is basically this piece here, you might get some kind of response like this for the input return loss. But if you're trying to cover multi-octave bandwidths, basically cascade the whole section of them, a number of them, and that's basically what you're getting in here. And this is done based on a Chebyshev polynomial, and that's very similar to deriving a filter transfer function using Chebyshev. And that's what you can see in here. You can see this is a fourth order where you get 4 poles, basically 1, 2, 3, 4 poles, and you can cover much more bandwidth than a relatively narrow bandwidth. And of course, always the bandwidth we're talking about is the upper frequency minus the lower frequency divided by the center frequency. Okay, so just have that in mind. The layout of this here, usually it's done like this, where we use the rounded implementation. So we basically come in with a 50 ohm, the output is 50 ohm, and we might have a divergent line like this with 90-degree bends so that we can spread it out so we can connect connectors easily and get access to this. And usually these cascaded lines, when you solve the polynomial, the Chebyshev polynomial solution to this, you come up with, it turns out that the impedances in here starts out from high impedance all the way to near 50 ohm impedance. And all of these are quarter wave lines, okay, meaning the distance from the middle of this 50 ohm line to the isolation first resistor, this section, this arc in here is usually a quarter wavelength, okay, at the center frequency. And so you've got a whole number of them, and then the resistors are always obtained from these computer-aided design tools or from table lookups, okay? So this is what I'm going to do today is I'm going to do 2 examples based on this. I'm going to do one from 2 to 6 gigahertz and another one from 2 to 18 gigahertz and show you some of the challenges in these designs. They're not trivial. The theoretical design work is easy, simply done by table lookups or computer-aided design apps. But when you go to the implementation, if you model it, you realize it gets much more difficult, especially if you're talking about frequencies above, say, C-band, above 6 gigahertz or so. Now, the layout of this, as you can see here, like I said, this is basically a typical implementation where each section is implemented as a cascaded. These are two arcs, one arc in here and one arc in here, and then there is a resistor in here. Now, the surface mount resistor in here, if you're doing surface mount, if you're not doing thin film implementation, be it strip line or microstrip line. Now, the length of this resistor and the parasitics of this resistor, it turns out really it's a big deal because that's really what limits the performance of these splitters for a broadband case. And you can see here, here's an example of how the layout of this basically is just you come up with this artwork where this is a quarter wavelength sections, and you can see we started out with narrow width lines, meaning high impedance lines, okay, all the way to near 50 ohm, or in this case, these are 50 ohm in here, but this one here is near 50 ohm lines, okay? And so the design of this, when you go to the layout, you start out basically with an arc that is from the middle of the 50 ohm in here up to here, that is a 90 degree. So you specify the radius and the angle of this, and you get that. And then you copy the same one, mirror image it in here. And that gives you a complete semicircle that includes the back off, so you can have a spacing for the mounting this surface mount resistor in here, okay? Now, like I said, the analysis of the multi-section broadband Wilkinson dividers is based on the theory of you could go back and split treat this with an odd and even modes, where you can basically terminate it by short, that's for odd, and by twice the characteristic impedance on this port, and start computing the reflection coefficient for both this circuit and this circuit for both modes. So the multi-section quarter wave transforming network optimized through the use of chip-chip polynomials. And then, you know, in the, like I mentioned before, for when we started out, when we took a graduate course, master degree level, we usually derive this, but now practically we just go to resort to tables and to computer-aided design apps that are available from various sources. The ones I'm going to use today is available freely from Microwave 101, and I'll show you, and it works very well. It's based on the chip polynomials. Now, these impedances can be obtained from the tables for cascaded lambda over 4 transformers, okay? Now, the even and odd mode reflection coefficients is basically how the principle of this is done, okay? Now, as an example, and it's almost everybody that took a course on or took some covered this in graduate schools, you usually really always resort to this paper here by Seymour Cohn, and this was done 1968 when I was 2 years old almost. So, and this paper in here really covers a lot of this material. Let me just show you this paper here. I got a copy of it. It's floating online. You can find this in a lot of places. So basically, he derives the multi-section quarter wave transforming sections of the two-way splitter multi-section. And then he even gives you some tables in here where you can see what the order is and the ratio of the upper frequency to the lower frequency. And he gives you, as an example, he gives you 2 sections, 3 sections, 4 sections, 7 sections. And he gives you both the isolating resistors and the characteristics impedance of the quarter wave line sections. And he does some examples in here. It's a very useful paper for you if you like to. As I said, this is the odd and even reflection coefficient derivations that is usually done. And he gives some examples in here and performances at the time. And one thing good is also he refers to other tabulated results for this concept, okay? All right, so let's get back to this. So now that's basically some of the technical backgrounds. The layout, the layout for when you start out a design, what you end up with is a bunch of quarter wave lines in here. But really, you have to transform this into an artwork like this because that's what you really need. You need a curved or semicircle based design so you can have a spacing for the surface mount resistors, okay? And these resistors in here play a big role because depending on the size of these resistors, and in here I'm listing some of these sizes that I had some available models for in the ADS Pathwave CAD system. And these are available from AVX. Okay, this is the CR series SMT resistors. So you can have 0402, which is 40 by 20 mils, or 60 by 30 mils, or 80 by 50 mils, or 120 by 60 mils. And usually the reason why would you use, of course, the smallest, tiniest resistor you can have is really what gives you the lowest parasitics that would limit your upper frequency. And that's what's desirable. But of course, that has the power dissipation of that resistor is very low, milliwatts. Okay, so as soon as you start trying to split higher and higher powers, you would have to use larger package resistors, okay? Now, so let's take a first example, okay? Now, the first example, what I'm going to do is I'm going to attempt to design a 2 to 6 gigahertz 3-section broadband Wilkinson divider, okay? And what I'm going to use is this app here. This app was available from I don't know why the logo here didn't show up here, but these apps are available from the people from Microwave 101. Just type microwave101.com, you can find them. And they basically, it's an Excel sheet. So you come in here, you specify the order, and you specify the center frequency, the bandwidth, and the sweep edges of the frequency for this case here. And then it basically it gives you a solution for the 3 lines. They give you even a diagram in here where you can start out. You can see that it gives you the resistors, so you work backward this way from R1 to Rn and from Z1 to Zn. So it gives you the solution for all of these, and it gives you the frequency response, okay? So that's basically what I'm going to attempt is to model this and see how this works out. And it works very well, so you can see that. So as a first example, I started with this where we got, okay, the oscillating resistors is 386 ohm, 102 ohm, 107 ohm, and the lines are from 57, 70.7 to 87. Now, of course, when you get this, you can go to the ADS, okay, and we start out, we put this on the system. So you end up with these resistors in here. We end up with 3 lines, of course, it's symmetrical, and 3 isolated resistors, okay? And when you model this, basically, the result is very good. So it's from 2 to 6. These are the return losses in here on the 3 ports, and the isolation is pretty good. The S21 or the transmission coefficient, it's very good as well. So you can see that from 2 gigahertz to this one is good. So this is good. Now, of course, I define these. You define the variables first. You define a variable, which is the 3 isolating resistors. with the transmission lines, okay, the 50, 57, 87, which are solution from this table here. Okay, these are the 57 and 87. And so and then of course the substrate I define in here. This is duroid 20 mil. Okay. But now when you look at this is really here. Now, essentially what you want to do is you want to come up with a BC board out of this. And the way this is right now, if you go to the layout, is just a bunch of lines, and that doesn't do you any good really, because we really need to have a circuit out of this, and this doesn't work. Okay, so and in that and really what you want to do is take this here and transform it to something that can give you a splitter like this, for instance, in this type of work. And that's where you have to utilize your engineering skills. So as a first, what we want to do is, if you look at this closely here, out of this, so what we're going to do is we're going to transform each one of these sections to a network like this, where we come in, we have two arcs, one arc for this one, and many people do it different ways, but the simplest that I found how to do it is usually like this: is you start with, you make an arc here, you make an arc here with a total length of a quarter wavelength, and you make it shorter by the length of that resistor, half of the length of that resistor, because you want to make sure that the arc in here and the arc in here leave out enough a room for the for the surface mount resistor to be sorted in there. And to figure out the length of this arc is really back to the high school level math. If you look at an arc out of a circle, out of circumference of a circle, which is 2 pi r, so it's just 2 pi r times the ratio of the angle, as opposed to 360 degrees, okay? So the length of this arc basically is really the angle times pi 1/80, which is normalizing this back to degrees, time the radius. Okay, the radius is this here, really, from this point to this point, or from this point to this point. And to start out, for our example in here, we're doing 2 to 6 gigahertz, so the center frequency is 4 gigahertz. So, and that's, if you solve the quarter wave 90-degree of it's usually with this duroid 20 mil, it's 13.9 millimeters. Okay, so what you want the total length from here to the middle of this 50 ohm line, that to be quarter wavelength, which is 13.91 millimeters. And so therefore now you have to subtract from that is half of the length of this resistor. This resistor in particular case in here is 2 millimeters. So half of the 2 millimeters is 1 millimeter. So 1 millimeters plus 2 arcs, okay, that should give me 13.9, which is a quarter wavelength. And of course, the angle is 90 degrees in this case for each arc. And the solution for this was that the radius is 4.109. And that's what I have in here for these arcs, basically, 410 for all these arcs. And these two transmission lines in here, they're the same impedance as the 90 degree, and they are basically the offsets that makes the arc, gives you this distance in here, okay? And that's what you get in here. So if we run this, this is basically what we have. Okay, so we have 3 sections. There's like this, and there's a spacing for every one of these 3 resistors, okay? And if you run the this here, the performance it's perfect. It's very similar to what the what the app computed. This is not really simulated. It's computed based on Chebyshev polynomials. Okay, and so it's very similar. So let's go back to here. And so we have this. So we're going to go to the next one, which I did here. Oh, okay. This is basically doing it for us. I did a single section, and that's what I just said. So you do a single section. And if you go to the layout of this, of course, this is the layout for this one here. Okay, so basically you end up with, this is the 50 ohm line, okay? You end up, this is an arc, and this is the line, okay? And this line in here really is what enables you to come in here to this package resistor in here. This is an 0805 resistor. And then, of course, you have the output case in this case. So you can have a lot of times we can separate the output a little better than this. We do this way, okay? And you can come back and create a pad for the 50 ohm if you need a wider pad, okay? And this is symmetrical, same network in here, okay? So let's look at repeating this for the 3 sections. And that's what we have here is basically, we've got the 3 resistors in here, ideal resistors in this case, ideal resistors. And what I did in here is these are each section is done like this, okay? So, and if we look at the layout of this, this is the layout for this one, okay? So we've got the 3 sections, all the you can see all the things in here. And so the other thing you can visualize now is look at this. You can start out with a higher impedance in here, a little bit lower impedance, a bit lower impedance, up to when you get to 50 ohm in here. Now you have to pay attention to this here so that the isolation is good. So you might want to move this here and still make sure that you have distance to solder the isolated resistors. So we can put this back here. This is the additional 50 ohm feed output feed lines, okay? All right, so let's, now the other issue with this is that, let's go back to the schematics of this. If you simulate this, okay, let's simulate and make sure that we have, the response is perfect, okay? The return loss is below 20 dB, the isolation is more than 20, and the insertion loss is pretty good, 1/10 of a dB for duroid, for this length, okay? But these resistors in here right now, I'm assuming they are ideal really. I'm not including any parasitics, and that's not really truly what happens. So what we need to do is we're going to go in and actually replace these resistors with a linear model that is available for some resistors in here. In this case, I started out with this package in here, an 0805 resistor, okay? And if you, as soon as you insert those in there, if you look at the frequency response of this, it's really a little different. You can see that the first of all, the return loss is good. It's a little narrower, okay, and the isolation is worsened a little bit. It's below 15 dB, and then the ripple or the roll off is pretty high in here. So you've got about more than 0.5 dB of insertion loss variation across the band in here. And that's because of the parasitics of this resistor in here. So what we're going to do next is shift over to a smaller package resistor. And this is an 0402 package, okay, these resistors. So, and when we run this, of course, so all of these resistors right now is an 0402, same values. We didn't change anything. So, and this, we would expect that we're going to get less parasitics, and we'll, yes, we do. So we're back. The return loss is below 20 dB. Isolation is below 20, and the insertion loss is pretty good. It's very flat transmission coefficient. And of course, the layout of this is still very good. The resistor is smaller, as you can see. So, and that enables you to do this very well. Now, let's get back to this. So we did this where we took ideal 50 ohm resistors. Okay, and then we put 0805. We realized that the parasitics have deteriorated the performance. We replaced that with 0402 40 by 20 mil packages that are available also. And then we get better response, okay? Now, of course, you really gotta, before you fab this, what you can do is you can EM this. And the way to do this is we wanna take this layout and put it into an EM simulator. In some cases, we would take it to HFSS, but in this case, I didn't do it, but you can do that as well. And you can actually, in fact, simulate the impact of the cover lid of the housing if you want. But I stayed with ADS and I said, okay, let's EM this. And let's use the technique of what we call layout lookalike EM model, where we take this, mesh it. I got rid of the resistors in here. And what I did is I made ports on all of these. You can't see the errors in here. I'll show you in a minute on the ADS. But you can see that this is a 9-port device in here, one, and of course there's 6 in here, there's 2 in here. And what we do is we create a model based on EM. And now we're not talking anymore microstrip sections. We're talking about an EM model of the whole thing. And then we come in here and we bring, we make a schematics out of this where this EM model is actually combined with the actual frequency response of these resistors, surface mount resistors. And then we sweep it and we can see that we can visualize the impact of that. It gives you more accurate, and that's another way that you could do to actually predict the actual performance of the circuit when it's laid out. Now, one thing you want to make sure when you're doing EM, of course, for both HFSS and ADS is that you're doing the meshing correctly, because for curved shapes, the meshing CAD systems really, you need to make sure that you do the correct settings so that you don't get this scenario in here. As you can see here, the meshing transformed the curved lines into a set of straight lines, and you can see that it interpolated the actual physical dimensions of this, and you can get inaccurate results. Now, after you do this, the settings correctly, and you can see that the meshing now is following the curved lines, and now you're not really skipping any copper. You're meshing the whole copper, okay? Now, once you do that, you can, of course, you're ready, and you can, generate the Gerber files for this system. So let's see how that is done on the ADS system. Let's just close some open files. Okay, so we can come in here and let's see, here's the schematics. This was done for the, okay, this is the 0402 packages. Now, here's the system where basically you take out this, I took out, let's see, I'm sure I'll show you here. So this is basically what I did is you take out this artwork in here and you put ports onto it, input port, and you put output ports in here and in here, and then you put ports also in here. This is for the actual resistors. And when you look at this, this is basically a, as you can see, it's basically a copper work, and then we run this, we mesh it, and we run the EM, and we create a model, and that model basically creates a symbol that is like this, where you can see the ports. And then once you do that, you can bring it into the schematics, And in this case, I brought it into the schematics that already has this in it, okay? So all I did is I attached these resistors in here, okay? These resistors are attached that are linked to the model of these package resistors. And what you get then is you get the performance. And in this case, the performance, let's see. Let's go to this. Okay. Okay, here's one. Okay, so this is really the performance of this. And you can see right away, you can spot that there are some issues. Okay, so this is the one that is not based on EM model, and this is the one that is based on the EM model. So you can see that the return loss is not very good. Okay, so and that due to some issues. So then in that case, you need to go back and work on this a little better. Okay, so this is basically showing you some of the issues that we're dealing with when you're doing a hybrid solutions like this. Now, let's get back to, okay, let me just show you how you do the artwork. So we're done with this. Let's not go to this one. And let's go back to any of these. So let's go back to here, for instance. If you need the artwork for this, you just go and you generate the artwork and you specify export, sorry, and you export it as Gerber in this case. And we want to view it. So, and that's basically what you're getting. Okay, this is the artwork, and this is, if you can go back and turn these off here just to look at the copper. So this is the top layer, okay, in here. And so you can check it and basically export this and give it to the fab house, and they can fabricate it for you. Okay. Now let's go back and work on another example. Okay, so let's work on another more challenging example. Let's say that we want to design a Wilkinson power divider with multi-sections, 7th order. And of course, how do you decide on the order of 7th order or 3rd order? I forgot to mention that. That's based on, that's a design criteria. Basically, it has to do with you, first of all, you know what the bandwidth that you're trying to cover, and that dictates how many sections. And in the table lookups and these apps, you can look at, you can figure that out. They give you the way there's an equation how to do that. So now this one is more challenging because, as you know, trying to get surface mount parts to operate at beyond, say, 6 gigahertz to 18 gigahertz, that's a challenge. And that's what I'm going to show you in a minute. Now, a lot of the papers and textbooks, they show you all these designs and tell you it works fine and everything. But really, in actuality, when you include the real model for the parasitics of the package resistors, you won't be able to get this to work across this whole entire band. Okay, so let's go back to the app in here. Here's the app. So I gave it a 7th order right now, and I gave it 10, the center frequency is 10 gigahertz, and the width is 16 gigahertz, okay? So, which covers literally from 2 to 18, okay? And it came back and it gave me basically all of these. So it gave me 7 sections of 90-degree quarter wave lines, okay, from impedances varying from 90 ohms to 55 ohms. And then it gave me 7 resistors, okay? And all the way from 506 ohms to 116 ohms, okay? And the frequency response is good, and of course, everything is nice on paper. And let's see what we really get in actual. So So that's what we're gonna get. And so the first thing we want to do is we put this straight without any bends or curves. I just put a feed line, input feed line, output feed lines, and then we put the 7 sections of a quarter wave line. We simulate them, and everything looks great. Okay, and let's just look at that. Okay. So let's get up here. We're gonna do, this is basically, so we came in, we defined the substrate, safe substrate. Okay, we defined vars for the 7 resistors for the 7 lines and the 90-degree length. In this case, it's 4.5 millimeters. And this is, we draw this circuit in here, and when you simulate this, of course, it becomes perfect. Look, from 2 gigahertz to 18, even to 21 gigahertz, everything looks fine. Isolation is fine, better than 20 dB. Insertion loss is pretty good, okay? But of course, this is really ideal right now with ideal resistors. Yeah, now real lines, real transmission lines, microstrip lines, but really we don't have any of the curves or any of the transitions to make this circuit. So as soon as we include, well, we have to transform first into this topology. So we add these 2 line sections to offset space for the resistor. And then we have the arcus, which is a quarter wave length, and in this case, it's 1.42 millimeter each one of these arches. Okay, so we put that on here, and we put the ideal resistors, and we still get very good response. Okay, and this is the layout. Now realize one thing, that the first thing that comes to eye is because the substrate is 20 mil, that's a little high for this frequency band. The quarter wave lines become very small. So, and you can see the impedance is varying from high to low, near 50. And you can see how wide the 50 ohm becomes compared to the size of these rings. And so, therefore, that's one of the things that when you look at this, you might want to say, you might resort to actually using multiple of quarter wave lines, because it's essentially the frequency response is the same thing, whether you use 90-degree or 3 times the 90-degree. Okay, it's the same thing. If you use 3 times, if you increase it by 3 times, then you get larger resonators in here, and that becomes much better. So now this works beautiful, but as soon as you put in the real resistors in there, and that's what you get, as you can see in here. In this case, I put in, these are 0805 packages. And as soon as you put those in there, the response has deteriorated, and it's pretty bad. Now you can, of course, how to prove to yourself that it is a resistor. So you can actually open these resistors, cancel them in simulations, and just leave it out as a T transformer, T-Junction transformer with 7th order. And that's basically, when you look at this, wow, you get back to being good. So you can see that it's a true 3 dB splitter across the band from 2 to 18. But of course, we don't have the isolation resistors. So the return loss on both of these 2 output ports is only 6 dB, which is a T-junction, okay? And the isolation is 6 dB. So everything works well. The input return loss is well matched, okay? And so let's just show that, proof that that is the case. So this is the network after we plot it, and these are all ideal resistors, okay? And we simulate this. Let's take a little longer. So everything is fine with ideal resistors. You can see that the return loss is pretty good. The isolation is pretty good, okay? And now let's look at the layout. The layout, of course, is right here. So we're very good. So we've got all these, and these ones in here, we might separate them so we can, everything looks good, okay? Except now, when we go and stick in these real model resistors, okay, based on this 0402 packages, of course, the response becomes a little bit worse. So you can see that this the parasitics have really shut this down, and you can see that the performance is not as expected, okay? And so to analyze this better, of course, okay, another different package, and we see the same. Okay, and now to analyze this, so let's do this. So, or let's talk first on this. So why is this happening? Okay, now why is it happening? Is because if you look closely on a resistor at the microwave frequencies, this resistor in here, it's not just a simple resistor, and this is for the thin film surface mount resistor from Vishal. You can see that this here has some inductances and has some parasitic capacitors to ground from both sides when you lay it on the board. And then it has this, and this network in here, the frequency response of this network at DC or low frequencies, you can see that it's pure resistor, this resistor value in here. The x-axis on these is the magnitude of the complex impedance to this resistor. You can see it's 1 in here, meaning that's pure resistor all the way up to, say, this is 800 megahertz, or no, 700 megahertz or so. And then beyond that, it's really going to behave depending on the resistor value. It's either going to be dominantly inductive or capacitive or inductive. And that's due to these parasitic things in here. And that's really what made this deteriorate, is because you're trying to get these surface mount 0805 packages to work up in these frequency regions, okay? And so we get an issue with this. And the way to prove this to yourself is I took one of these resistors, 510 ohms, okay? And then I took the an ideal resistor, 510 ohm, just value. And then the actual model that is provided by the Pathwave system. And this model, and when you look at the frequency response, you look at the real, you sweep this here. Of course, this is 510 ohm in parallel. When you look at the input impedance on this port, this one is in parallel with the 50 ohm, and you end up with some kind of 45 ohms, okay? So if you look at this, look at what happens. This is the real part of the impedance looking into this versus the complex part, okay, the imaginary part. And you can see that as you come in to 4 gigahertz, you're getting a real resistor, but beyond that, you're starting to get capacitances, and that's what you're getting in here, all these capacitances. And you end up with, say, only 25 ohms at the upper frequencies where we were operating. And that's part of the issue, okay? Now you can go, this one here is an 0805 package, okay? But if you go to smaller packages, okay, you can see that up to 10 gigahertz, this is 0402 package, and that's basically specified in here. This is the manufacturer gave you this code here, 510 versus 1220. That shows you, there's a table in here, it shows you what the dimension, what the package is. In this case, the previous case was an 0805 package, okay? And in this case, it's the code of the package is 510. So that is right here. That's a 0402 package. You can see that the parasitics are good up to 10 gigahertz, okay, when you go to 0402. And that's trivial. That's natural. It's smaller package. And as soon as you go beyond that, it starts deteriorating, okay? And that's basically what happened. If you put 0402 packages, you get a little better response than you would get when we had this one here, an 0805 package. So you can see the frequency is just went off cliff, okay? So, so that's what, let's look at so that's what I did in here is if you see, I put in this, this is from the library in here,
this one here is from with this part number, okay? And we sweep that, and you can see right away that you would get this type of performance where the real part becomes, instead of being a straight line, 45.5 ohms, it diverges from that because of this capacitance, parasitic capacitance or package capacitance that is in here. And you end up with this, of course, it's pretty bad, okay? But of course, if you go to a smaller package, the response is a little better, okay? And that's what you see in here, basically, because of the package capacity. So, so what have we learned with this? That multi-section Wilkinson dividers, if you're trying to cover, let's say, from 2 to 18 gigahertz, it's pretty difficult with packaged resistors. Just a few conclusions. So the isolation resistors need to be thin film packages to minimize the package parasitics. The quarter wave transformers, when you're trying to cover something up to 18 gigahertz, has to be really use multiples of quarter waves instead, so that you enlarge it, so there's more control. You get more losses, but that's still better than you getting into issues where you get primary modes being generated and so forth. And also the size, especially if you're dealing with a thicker substrate. That's the other issue. 20 mil duroid is probably you want to go lower, thinner than that. A better approach to do these splitters is by using a strip line instead of micro strip line, and then using a resistive sheet from Quantictizer, basically. And that you can go to this here, and you can learn how to do these strip line resistors, embedded resistors, instead of doing this. And the trade-off with that, of course, is you're dealing with a strip line, so therefore now you need the input and output axis is not anymore on the top layer, so you either use a transition from microstrip to strip, or use one of these sophisticated edge connectors that can connect to the. So I hope this is. I hope this gives some kind of ideas on the challenges of designing broadband Wilkinson power dividers. Again, this is Dr. Mohamed Nezami, an independent consultant. You can reach me out for any design work. I'm a freelance designer, basically. So until the next video, I thank you for following this. Please go ahead and subscribe to the channel. I would appreciate that, and hit the like and share it if you could, so that others benefit with this, okay? Well, until the next video, I thank you very much and have a great day. Thank you very much. Have a good day.